inclined planes! Ah! Okay, so an inclined plane is a tool used to move objects from one height to another. Allows for the movement of an object without lifting it directly against the gravity field. Let's say I had a box here and I wanted to raise it up to there. Well, it'd be hard to do that because I have to go directly against the gravity field. Here I've got a much longer, smoother incline, just like we use for people in wheelchairs to get up inside of buildings rather than lift them directly up against the gravity field on the stairs. So the weight on an inclined plane is as follows. Excuse me, I'm sorry. So you can see this is the vector that represents the weight of this particular block on this black line, which is an inclined plane. As I tip the inclined plane up, what happens is the weight is broken naturally into components by the incline itself. Some of the weight acts onto the plane, and some of the weight acts parallel to the plane. And you'll notice as we tip the incline up steeper and steeper, more of the weight acts parallel to the plane and less of the weight acts onto the plane. You can see it increasing as we move to a steeper and steeper angle. In fact, if I got to 90 degrees, all of the weight would act parallel to the plane. So, how do we calculate this? Let's consider the forces. The perpendicular force, that is the force perpendicular to the plane, we call it onto the plane, is calculating using cos. Fg cos onto the plane. That's what the O stands for. So you remember, theta being the angle of the incline here. So it's equal to the normal force because the plane pushes back with a force equal in magnitude and opposite direction of the weight component of that force. Parallel to the plane, we have a force that acts parallel, and we remind ourselves of that by using this calculation. Fg sine parallel line, sine theta. Sine is the angle here. Again, theta is the angle of the incline, and the parallel component of the weight acting parallel is Fg sine theta. It's generally equal to the force of friction. For an object that's in equilibrium, whether it's in static equilibrium or dynamic equilibrium, the parallel force to the plane is usually equal to the frictional force, Ff. So, what's the essential knowledge? What happens to the component of the weight that points onto the plane as the angle is increased? Well, as we're increasing the angle, the cosine is going to decrease. What happens to the component of weight that points parallel to the plane as the angle is increased? Well, as it's increased, the sine of that angle increases. The force parallel increases. What happens to the normal force as the angle is increased? Well, since the normal force is directly related to the cosine, as the angle increases, the cosine decreases, so the force perpendicular to the plane or onto the plane decreases. Finally, what happens to the frictional force as the angle is increased? Well, although the parallel force increases as you tip it up, the frictional force actually decreases. The reason for this is that it depends upon the normal force, which is decreasing as the incline is tipped steeper and steeper. Let's try a problem, shall we? Here we have a box with a weight of 50 newtons on an incline that's angled at 30 degrees. And you'll see the essential three forces. The weight acting perpendicular to the earth, straight down. The normal force perpendicular to the plane. And in this case, we have a force acting up the plane. It's probably the force of friction. So what is the normal force? To calculate it, we use Fg cos theta. Cos onto 43.3 newtons. If the box is sliding with a constant velocity, what is the magnitude of the frictional force? Well, by constant velocity, we know that this box is therefore in dynamic equilibrium. It must be equal to the force parallel to the plane. Fg sine theta, sine parallel line, 25 newtons. And that's the inclined plane. It's not that hard. You just have to remember cos onto and sine parallel line. See you in class, gang.